Welcome back. In this video, we will walk through the proof of the Nordhaus-Gaddum Theorem, which establishes two bounds on the relationship between the chromatic number of a graph and its complement. So it gives us information about those two things, and we have both a lower and upper bound for the sum of the chromatic number of the graph and its complement, and the product of those two numbers. So a couple things to keep in mind here that we're going to use along the way is one, theorem 14.19, which says that for every graph G, the chromatic number is at most 1 plus the maximum over all subgraphs of the minimum degree of that subgraph. So that's one thing to keep in mind. We're going to use that. And then the other is a result actually from analysis, which is that the geometric mean of two positive real numbers never exceeds the arithmetic mean of those same positive real numbers. So that is square root of r times s, that's the geometric mean of r and s, right? R times s to the 1/2 is less than or equal to r plus s over 2. All right, so what we're going to do first is actually establish this bound. We're going to show this bound first, and then this is going to imply this lower bound as well over here. So how do we get this bound? We're going to produce, so let's say G and G complement are order n. We'll produce a coloring of Kn, and let's say chromatic number of G is equal to K, and chromatic number of the complement of G is equal to L. We're going to produce a coloring of Kn using KL colors. That many colors, K times L many colors. From which it'll follow, right, this gives us that the chromatic number of Kn, which we know is n, but we'll have, using K and L, we'll produce a coloring of Kn, and so that means this chromatic number is at most K times L, and that is the product of chromatic number of G times chromatic number of G complement. So that's the idea, is we need to produce a coloring of Kn using KL colors. So we let there be a coloring of G using K colors, the chromatic number of G, and a coloring of G complement using L colors. And then assign, so now in Kn, assign, so let's say this coloring of G is, let's call this C. This goes from the vertex set of G to the integers 1 through K. And then let's say we have C prime here from vertex set of G. Again, vertex set G complement is the same as vertex set of G, 1 through L. And now, again, we're dealing with the same vertex set. It's just in Kn, all of the edges are there. So assign each vertex, let's say U of Kn with an ordered pair. So we're actually going to, usually we color using the integers 1 through K. Here we're going to come up with a coloring using ordered pairs. With the ordered pair C of U, C prime of U. All right, so what does this look like? Let me look at an example here. So let's say G has six vertices. G complement has 6 vertices. So I take a coloring of G. So let's say that would be, let's do a coloring of G. How about 1, 1, 2, 1, 2, and maybe 1 again. So there's a coloring of G. And let's take a coloring of G complement here. Let's do 1, 2, 3, 1, 3, 3 for this one. So here, chromatic number of G is 2. Chromatic number of G complement is 3. And then in the coloring of K6, so this vertex here will be assigned the color 1, 1. This one will be assigned 2, 3. Here we'll have another 2, 3. Wait a second on that. Right, so there's some issue here. Give me 1 second. Right, so try and notice my mistake here. I did make a mistake in making these graphs. And that mistake would have ended up with, I would have had 2 adjacent vertices in K6 being colored the same. So there was some issue there. What went wrong, I don't know if you noticed this, it took me a second to realize my mistake and hopefully learn something from it, is that here, there's no edge here between these 2 vertices, and there's no edge here between these 2 vertices. But this is supposed to be a graph and its complement. So actually what I'm going to do is I'm going to let this be an edge, and I'm going to change my coloring. Now I have an odd cycle in here, so my chromatic number of G is 3, and I'll color this one 3. And then this will be a non-edge there. And notice that means that since now this is an edge, that means I need to color this something different in the first coordinate in K6. And now I'll have a 3, 3 here instead. Up here I'll have 1. So yeah, I couldn't, I made another little mistake here. I had this be 1, 1. This should actually be, say, a 2. And now because those 2 vertices are adjacent in G, that means they have to be colored differently, which means their first coordinates in Kn have to be different, and so the ordered pairs are different. All right, let's keep going through and see if I can uncover any more mistakes I made. 1, 3, this, and then over here I would have 1, 2. So, right, notice that this is now a proper coloring of Kn. And the idea here, why this always produces a proper coloring of Kn, is because either the 2 vertices are adjacent here in G, in which case the first coordinates of the pairs will be different, or they're adjacent in G complement, in which case the second coordinate of the pair would be different. And that would, in any case, either G or G complement, we would have the ordered pairs have to differ in at least 1 coordinate, and so the ordered pairs are different. And so we'll have a proper coloring of Kn in general. And so that produces, this gives us a KL coloring of Kn, which gives us this inequality here, and tells us that N, so in conclusion, N is less than or equal to chromatic number of G times chromatic number of G complement. Now I'm also going to take down another one of these inequalities. Remember that the geometric mean, so if I take a square root here, I'm going to square root N less than or equal to square root of chi of G times chi of G complement. That will be less than or equal to the arithmetic mean of G and its complement over 2. And rearranging this a little bit, we get that 2 square root of N is less than or equal to the sum of the chromatic number of G and the chromatic number of G complement. So that not only takes care of the lower bound in 2, but also takes care of the lower bound in 1. And so now we'll take a stab at the upper bounds in each of these. And for this, we'll first show this upper bound and then use that geometric arithmetic mean property to deduce the product. All right, so why is this true? Well, we're actually going to use this, this theorem 14.19 that the chromatic number of G is less than or equal to 1 plus P, where P is the maximum over all subgraphs H of G of the minimum degree. So P is the maximum of all the minimum degrees over all subgraphs. And my claim here is that if that's the case for G, that if P is the maximum of the minimum degrees over all those subgraphs, then the minimum degree of every subgraph of G complement is at most n minus P minus 1. From this, it'll follow, right? That'll tell me that the chromatic number of G complement is less than or equal to n minus P minus 1. And then it'll follow, by our assumption, chromatic number of G's here, plus chromatic number of G complement. This will be 1 plus P plus n minus P minus 1. That this will be of every subgroup is at most n minus P minus 1. Right. Another little mistake here. Again, this is, I always like to leave these mistakes in here just because they're good learning moments. Right, so here I said chromatic number of G complement was at most n minus P minus 1. I thought that followed from the minimum degree of every subgraph of G complement to be n minus P minus 1. But recall, yeah, I mean, it's right here. Theorem 14.19 says chromatic number of G is at most 1 plus this. So it follows that the chromatic number of G complement is this plus 1. And so that's n minus P. And then it'll follow, so that's 1 plus P plus n minus P. That gives me the upper bound of n plus 1. That'll be my upper bound. So that's what we're going for. Again, I want to show if, right, the maximum of the minimum degrees in G is P, then the maximum of the minimum degrees in G complement is n minus P minus 1. So suppose not. Suppose that's not the case, then let H be a subgraph of G such that the minimum degree of H complement inside of G is at most n minus, or is at least n minus P for the subgraph. So this is the minimum degree inside of the subgraph H bar in G bar. And so every vertex of H has degree P minus 1 or less in G, right? If this is the case in H bar, and these are the degrees in G bar, at least n minus P, do n minus 1 minus n minus P, we get degree at least, or at most degree P minus 1 in G. Now this number is important here, that every vertex of H has at most this degree in G. But remember that P is the maximum of the minimum degrees over all graphs F in G. So I'm going to let F be a subgraph of G with minimum degree of F equal to P, right? I know P is the maximum, so I'm actually going to find that subgraph with the maximum minimum degree in G. So every vertex in F of F has degree P or more in G. So compare that up here. Every vertex of H has degree P minus 1 or less. Here we have degree P or more. That means that F and H are disjoint sets of vertices in G. Right? No vertex of F belongs to H. Now the order of F, since every vertex of F has degree at least P, the order of F, number of vertices there, is at least P plus 1, so that every vertex can have degree at least P. And that follows then that the order of H is at most n minus P minus 1, right? N minus the number of vertices in F, since these are disjoint. However, this contradicts the fact that this fact up here, that the minimum degree of H bar in the complement is at least n minus P, right? So if the order of H is at most n minus P minus 1, then the minimum degree in the complement would be at most n minus P minus 1, and so that contradicts this assumption. And yeah, so that's a contradiction, and so it follows that our claim was true. Right, our claim is justified now. Sorry, computer's lagging a little bit. From which it follows then that chromatic number of G plus chromatic number of G complement is n plus 1. And then remember that this geometric arithmetic mean business, I'll put this maybe down here. So we have square root of chi of G times chi of G bar is at most chi of G plus chi of G bar over 2. And this is now less than, or by this up here, this is less than or equal to n plus 1 over 2. Squaring this yields chi of G times chi of G bar less than or equal to n plus 1 over 2 squared. And that finishes the proof. Now we have all of the bounds that we set out to prove originally. So we have some nice information about how the chromatic number of a graph and the chromatic number of its complement interact with each other through sums and multiplication. So one thing I'll point out here after this theorem is that this is actually best possible. So why is this? Well, if n is any positive integer, and a and b are any two positive integers that satisfy the conclusions of the theorem, that is, this inequality is true, this inequality is true, then there is actually a graph of order n such that chi of g is equal to a, and chi of g bar, the complement, is equal to b. And so every possible number between any of these two bounds is achievable for a graph and its complement. And so how does this work? Well, we choose n1, n2, up through nk, and a. So once we picked a up here and b up here. So we choose a positive integers, n1 up through na, such that their sum, equal 1 to a, is my positive integer n, the order of the graph, and such that the largest number here, so I'll order these in non-decreasing order, n sub a, and let's say this highest number is b. So we choose b as our highest number in this list. We have a numbers. Now, this is possible to do because a and b satisfy these bounds. This is possible. And then the graph that achieves this is g setting G equal to the complete apartite graph with partite sets n1 up through n sub a, and remember n sub a is equal to b. Well, this is, or I guess so here's my graph G. That means its complement will be, each of these independent sets will become a complete graph in the complement. It'll be disconnected. So this will be what? K and 1 plus K and 2 up through K n sub A. So the chromatic number of G, well, that's a complete multi-partite graph. There are exactly a partite set, so the chromatic number of G is A, and then chromatic number of G complement. Well, G complement is a disconnected graph consisting of a bunch of complete graphs, and so this will be the maximum. Chromatic number of G complement will be the maximum of the chromatic numbers of each of these complete graphs, and that will be achieved here, Kn sub A. That's, of course, K sub B, which has chromatic number B. And that gives us exactly what we want here. Okay, that's it for this video. I'll see you next time.